So now that we know what a definite integral is, it's time for us to learn some properties that apply to them. This first one here, if I have the integral from a to a of f of x dx, remember if I had a to b, then that was like it was interpreted as the area under the curve from a to b. Well, if I have a is the same, right, then I really don't have any area. So this is actually 0. So if my limits of integration are the same, or my bounds here are the same, then my value is just 0. Okay? So I have another one here that if I have from a to b of f of x dx, this is the same as negative if I switch the bounds and I put the a up here and the b down here of f of x dx. So they're the same except for by a negative sign. All right, so then we can also have the sum and difference of integrals. So if I have a to b of f of x plus g of x, right, and these are all with my dx, then that means, and I can put the minus here too, it could be plus or minus, then that means I can break them apart and do them separately. I can think of a to b of f of x dx plus the integral of g of x dx from a to b as well. So I can do them separately. So this is kind of like when we had derivatives and we had the plus and minuses between them, we could do the derivatives of each term separately. We can also do that with definite integrals. We can look at each term separately. There is also a constant multiplier rule. So if I have, for instance, some constant like c f of x, and I'm doing the integral from a to b of f of x, or I'm sorry, that's supposed to be dx there, then this is the same thing as if I can pull the constant outside. So just like when we do derivatives, the constant just sits there while we do the derivative. When we do definite integrals, the constant just sits there and we do the definite integral. So we can think of it like this. All right? And let's see, then we have one last one that basically says that if I have some integral from a to b of f of x, then I can break this apart into two different integrals. So I'm going to choose some value c that is between a and b, and that means I can go from a to c of f and add to it from c to b of f. So this was c is in between a and b. So essentially it's kind of like if I have some curve here, right, and I'm looking at this area and I know that here's my a and here's my b, and then I'm like, okay, well, I'm just going to choose some random c in here. Then if I add a to c and c to b together, I get a to b, okay, because a to c is this part, right? C to b is this part, but then a to b is the whole part, so I can just add them together. All right, so those are our properties of definite integrals. So let's look at this example here. So for instance here, this is an example of the last property that we were thinking of. I have the integral from 0 to 2, and I know that this is equal to 6. And then from 0 to 6, I know is 14, but we want to know what from 2 to 6 is. Okay, so we can think of it like, okay, so if we connect it to, if you think area under the curve, okay, so we know that from 0 to 2, if this is my 0 and this is 2, this is 6, right? And then if this is 6 out here, and I know this whole thing here is 14, because that's what this 0 to 6 says, then what does this have to be? Well, in order for this to be 14 altogether, this must be 8. So this is equal to 8. So we can, sometimes it's a little confusing when you look at the numbers, but if you think of it pictorially, it's a little bit more straightforward. Okay, so we also have the comparison theorem. So I have this f, right, and I have this g, and I know that g of x is greater than f, right, for all of this between a and b, at least, we'll call that. So it looks like further than that, but we'll specifically talk about a and b here. So if I was thinking of the definite integral then from a to b of both of these, then this comparison theorem is going to hold because the area under the curve of g, right, is all of this, right? Actually, I'm sorry, it's this part right here, right? Whereas so if g is bigger than f, right, and so then the area under f would be just this part right here. Clearly, this integral, this definite integral, is going to be larger than this definite integral, so the inequality will hold. Okay. All right. And then the last thing that we're going to talk about here is the average value of a function. Now, the average value of a function is just kind of like, you know, if you were going to calculate an average of, you know, three things, you had 2 plus 4 plus 6, right? Then you add these all up and you get 10, 12, and then you divide by 3, so your average is 4. This is essentially the same thing because really this integral from a to b is sort of you're kind of adding up the area, right? And then this is by, instead of having a specific like number of terms that we're going to divide by, we actually just divide by the number of units on the number line. So that would be just b minus a. So this is the same thing. It's like taking the average, but just of a definite integral this time. So let's use that here. Okay, to find the average value of f of x equals the square root of 9 minus x squared over negative 3 to 3. So I'm going to write the definite integral. That means I'm going to find the integral of 9 minus x squared dx. These are my bounds from negative 3 to 3, and then my number of units on my number line, I find that kind of like as b minus a. So that would be 3 minus 3, or actually negative 3, which is 6. So there's 6 units, so I have a 1/6 out here. So this is kind of, I'm using that constant multiplier rule. Like I have the 1/6 in here, but I'm just going to put it on the outside because it's a little less distracting. So I'm going to figure out what this is, and then in the end, I just multiply it by 1/6. Now, I really don't want to use the summation notation, so I'm hoping that this is a thing we can use geometry on, and it is, because again, it kind of, the square root of 9 minus x squared, you know, if you think this is y equals the square root of 9 minus x squared, then if I square both sides, I get y squared equals 9 minus x squared, so I get x squared plus y squared equals 9, which means I have a circle centered at 0, 0 with a radius of 3. Okay, now I want to go from negative 3 to 3, and the square root that's not negative means I'm going to have the top half of my circle. If it was the bottom half, it would have been this part, right? Okay, so I'm going to draw a picture here of this, maybe 1, 2, 3, 1, 2, 3, 1, 2, 3, and so I'm going to just draw the top half because that's all we need. So that means I'm going to have this here, which is a little bit lopsided top of a circle. I know that, let's see, this is positive 3 and this is negative 3, and so we want this whole part. I know we did a circle before and we only did a quarter of it. This time we have the whole top half from negative 3 to 3. So this is going to be, so right now I'm just trying to calculate this part right here, right? And then I'll just multiply it by a 6 in the end to find the average value. All right, so I know that the area of a circle is pi r squared. And I know that my radius of this circle is 3. So I have 9 pi, but it's half of the circle, not the whole circle. So I have 9 pi over 2. So that is just the definite integral. And then to find the average value, I divide by or multiply by 1 over the number of units on the number line, which was a 6th. So I multiply this by 1/6, and I get 9 pi over 12, which I could simplify to 3 pi over 4. And that is my average value.